Hi YouTubers, Dave out in Pennsylvania, USA. Stick with me for this short video. I have a section of nickel-plated graphite felt. This was put into a nickel chloride bath, and we went with potentiostat 4 volts. We let it go for about an hour and a half, and I will get from my student the additional information required. I'll also upload the dimensions of this section of graph. And here I am about to do a potentiostat constant current voltage, 1 amp, bring it up to 4.5 volts, cutoff 0.15 amps. Let us start. And you'll be able to see the information we get. Might be better to turn it this way. Won't be that long. Then I'll show you the step levels for power output. Still at 1 amp. Okay, now we're starting to drop. We're doing trickle current. Going to go down to 0.15 amps. This is for the benefit of those that are getting into this. Here is the electronic device, the load that I use, ZKE Tech. And if you want to do cycles of charge discharge, make sure you get model A10H. See the lower right? 20H will not do that. 10H. Okay, back to the charge. And I have this graphite in a series circuit with a couple of twin supercaps, commercial supercaps, rated at 2.8 volts, 100 farads each. They're in series, so we're going to get 2 times 1.8 or 2.8 or 5.6 volts. Because I don't have any parallel resistors in place, and I'm using alligator clips because I'm not moving it around, I'm cautiously stay well below that window of 5.6. You don't want to destroy your supercaps. And of course I need the supercaps there in order to be able to do what I'm doing with the graphite component, which they're being tested for use in a bench scale prototypical supercap. Okay, back to the charge. We hit the cutoff. Now you can see the open voltage, 4.35. Now I'm going to go to auto test, and you can see my input. I'll turn it this way. At the bottom, the parameter settings, and let's get this started. We're going from 1/10 of an amp to 1.0 amps, cutoff voltage 0.3 volts. And the steps are each 1/10 of an amp, and the interval is 10 seconds. Here's the first step with a feeble 100 milliamps. There's the voltage, and there's your power in watts, 0.4. Then we're up to 0.8, 1.2 for the third step. Going up, power output is the current's going up. So at 400 milliamps, step 4, you can see 1.5 watt output, 1.8. Let's see if we get a 2. More about that in a second. There it is. It's going to probably drop a little bit while hanging in there. Now, if you run the supercaps alone, which I'll do next to show you, without the graphite, which is offering resistance, the question is how much, we're going to have much power output, less resistance due to the graphite felt. This is a pretty good run. Oh yes. Now I've only run this one, this is the second time. This is the second time I've run this, just before I recorded this one. This is impressive. Now that has no DES, deep eutectic solvent with an electrolyte, and we find we use inexpensive DESs where lithium bromide dissolves. This is very good power output, and I'll put the dimensions down for this section of graphite. Now, the graphite felt is flexible, but there's a price to pay when you do nickel plating because it's going to make it more rigid. And the question is, by trial and error, to find out what's going to work for you in your application. We do light nickel plates where we just have a coating, and we'll be studying these by scanning electron microscope imagery because we want to get a trade-off between conductivity, flexibility, and of course the surface area is going to have to be delivered by, let's say, an activated carbon. Now I can either apply some activated carbon paste, or we will use materials such as this, activated carbon felt, which doesn't have the conductivity, but it offers the surface area. Very important in capacitance with supercaps. Those are good numbers based on what I've been seeing. Now, what I'll do, if I can do this with the one hand, let me disconnect this. And of course, if you're a beginner, get yourself disposable gloves, huh? You don't want to be getting skin oils on this. Let me hook these together. And now we'll have the series circuit of the supercaps, but there will be no graphite resistance. Let me bring it up to 4.4 volts. Back to single test. C-CV, amp 1.0. Let me make it 4.4 volts with a cutoff of 0.15. We're underway. So this is simply the supercaps alone. And in blue, you see your voltage or potential, and the red would be the current being applied. Constant current. I should say constant voltage, bringing it up, leveling off of 4.4, which we are, and now trickle current down to 0.15. So this is potentiostat, constant voltage. When I discharge, we do constant current. That's another matter. And we'll soon show you the step levels for comparison. Supercaps without a graphite component in the series circuit and the numbers with graphite. It will depend on the thickness of the graphite, the width, the length, the amount of nickel or cobalt or nickel-cobalt alloy deposition, whether you oxidize the graphite, whether you sonicate it, and then you're going to be applying a DES, let's say, with an electrolyte, and that's going to offer some resistance due to the viscosity of a deep eutectic solvent. So we're coming in close to 0.15 cutoff. Now let's see what happens with the open voltage. There we are. It's going to drop a little bit, not much. Not much. Now let's go to our auto test and get underway. Now let's look at these numbers. At first it'll be about the same, 0.4, because we're only going through 1/10 of an amp. So the first couple of indices won't be impressive. That might go to 0.7 or 0.8, okay. You can see your currents, voltages, and power output. Third step, 1.2 watts. 10 seconds. 1.5 watts. Now let's see if we start to see a difference here without the graphite's resistance. Fifth step, 1.8 watts. Dropped a little bit, 1.7. Now we're at 2.0. Remember, we maxed out with 2.0 with the nickel-plated graphite. Dropped a little bit, 2.1. That's for the 7th. 2.2 for the 8th. Increase power output. The 8th one, 9th one. 9th is 2.2. So we're racking up those 2+ values, 2.0 and plus. And the 10th one, see, is still strong. So this is a simple demonstration for my undergrad students and for home researchers or those wanting to get involved in energy storage, in particular supercap components. The electrode, graphite, is what I work with, felt and yarn. But as you use graphite felt and nickel plate, the key is to get maximum conductivity, but you would like it to remain flexible. And this is becoming somewhat rigid. Now we'll also be pasting expanded graphite on the surface of this. And if you've not seen it, I can certainly show it to you while I'm with you. This is a gift from Asbury Graphite in Pennsylvania. They have gifted me a wide range of their products going back a few years ago. I got this back 8 years ago. And that's what it looks like. Worm-like, a lot of air, very good conductivity. If you press that, there's a YouTube video where it can be pressed into a very impressive but very fragile electrode. And what I'm going to do is attempt to make paste of this in selected deep eutectic solvents with lithium bromide and see if we can boost conductivity that way by applying a paste to the graphite felt. There's a lot of different experiments you can do, and if you work with expanded graphite. Now, I'm not going to get into expanded versus exfoliated graphite, but you may have some graphene here. But basically, for our purposes, they're one and the same, the method and the material. But you don't want to be breathing that in. Okay, so a final look. And you could see that with the caps themselves, we had 3 2.0 or higher and a couple of 1.9s. And you saw that with the nickel-plated graphite, we were starting to take on a semblance of solid conductivity. The graphite felt without treatment, commercial graphite felt that I use, and there are different thicknesses, of course. We get 0.9 ohms per centimeter with a multimeter, and it's good enough that it can serve as a conductive material. And of course, I wouldn't recommend using alligator clips. You might want to do some soldering, but here I'm doing analyses, and this is how I get my students started, undergrads. And I'll be retiring in June, but continuing my research. And thank you so much for watching, and we'll keep you updated on our developments. I enjoy sharing our experiments with our viewers. Bye for now.